we would like to have a brief discussion on taking limits and the derivative of a function here. For a function of one variable, y equals to fx, if you want to find the limit of fx at x equals to x0, you are considering the value of the limit for the expression f of x0 plus h when h tends to 0. In order that this limit exists, we need that the right-hand limit to be equal to the left-hand limit, and they both gives a real number. Indeed, if you are standing on a horizontal line, you have two choices of walking towards a point x0. Either you walk from the left towards x0, or you walk from right towards x0. When we take the derivative of a function at the point x equals x0, it means that we are considering the value of the limit for the expression f of bracket x0 plus h minus f of x0 divided by h when h tends to 0. In order that this limit exists, we need that the left-hand limit to be equal to the right-hand limit, and they both gives a real number. Now, let us consider a function with two variables z equals f of x, y. If we consider the limits of the function at a certain point x0, y0, there will be more ways of approaching this point. You can imagine that you are now walking in a park and the point x0, y0 is the location of a fountain. In particular, you can walk towards the fountain from the east, south, west, and north. To say that a function has a limit at the point x0, y0, we need to make sure that in all the paths that you walk towards this point, the limit gives the same value. In this graph, we shall see that the function z equals x squared over x squared plus y squared has no limit at the point 0, 0. Why? First, we consider the path along the x-axis, the red axis. If you approach the point 0, 0 from the east or the west, the output approaches 1. Now, if you refer to the path along the green y-axis, you find that when you approach the point 0, 0 from the north or the south, the output of the function approaches 0. Since these limits do not agree, we conclude that the function has no limit at 0, 0. Now we consider that our function is differentiable, and we consider the paths of approaching a point from east, south, west, or north. This happens when we keep one variable as a constant and vary the value of another variable. When we consider the derivative of the function f of xy while keeping y as constant, we are studying how the output of the function changes with respect to x, and simply treating y as a constant. It is called the partial derivative of f with respect to x. Similarly, when we consider the derivative of the function while keeping x as constant, we are studying how the output of the function changes with respect to y, and simply treating x as a constant. It is called the partial derivative of f with respect to y. In real-life scenario, imagine that the production cost of a fan depends on the cost of steel and the cost of plastic. If we wish to know how the change of cost of steel, x, affects the cost of the fan, z, we will first treat the cost of the plastic, y, as constant and consider the derivative of the function with respect to x. As long as we treat y as a constant, let us treat this as y0. The function becomes a function with a variable x only. So the derivative is the same as having derivative to a one-variable function. If we visualize this in the graph, it means that we are considering one cross-section of the graph which is parallel to the x-axis. When we consider the partial derivative of f with respect to x, we are considering the slope of tangent line touching the curve AB at a certain point x, which belongs to this cross-section. Similarly, if we want to know how the cost of a fan depends on the cost of plastic y, we treat the cost of steel x as a constant. It means that we treat x to be a fixed value x0 and consider the cross-section of the graph which is parallel to the y-axis. When we consider the partial derivative of f with respect to y at the point x0, y0, we are considering the slope of tangent line touching the curve CD at x0, y0. There are several notations for having a partial derivative of a function z equals f of xy with respect to x. You can use the partial derivative symbol to express it as partial f over partial x of xy or fx of xy and so on. You can also refer to it as partial f over partial x or fx. Let's proceed to example 1 and example 2. Please refer to them by yourself. In conclusion, whenever you take a partial derivative of a function with respect to a particular variable, we treat all other input variables as constant. Please be careful with the notation when you are having a second partial derivative. For example, if you write it as fyx, it means that you first compute the partial derivative of f with respect to y, and then treat it as a starting function, and further take a partial derivative of this function with respect to x. When you use the partial notation in an expression, you will be writing x at the left of y at the bottom part.